Hi, in this video, we're going to take a look at using decision trees in supervised learning. All right, every single supervised learning project I work on, I always build a linear regression model or a logistic regression model and a decision tree. All right, so decision trees are really very simple models for supervised learning. They break things down to like a Boolean logic point of view, where one at a time, you look at a predictor variable, you decide if the value you're looking at is above or below a cutoff or within a certain set, and then you make a decision based off the tree, repeat with a different predictor variable or the same one until you reach your final answer. And so this is kind of like a sequential Boolean logic point of view to making a supervised learning prediction. They're easy to understand, easy to interpret, easy to read. You could use a decision tree without using a computer or a calculator. In real life, real time, you could actually take an observation and reach a predicted value without doing any math at all, except for reading a number and comparing to a cutoff. Uh, these are foundational tools for machine learning. Most of the time for actual supervised learning, honestly, we're probably going to be using these as an ensemble, like in random forest or gradient boosting, but these are still useful on their own, mainly because we get a really good graphical representation of our decision-making process, so it's easy to understand, and I can, so one thing I use these for is I will always build that decision tree and I'll just try and read through it and get a better understanding of how of the features in my data. So what's going on. And so as I build other models, I can build my model better because I understood what's going on with this simpler model. As like, for example, let's say that I'm going to be, doing a stochastic gradient boosting model or random forest or neural network or anything like that. Well, as I go through the process of that building, it's hard to understand what's going on with those models because they're more complicated. The decision tree is very easy to understand. So what I can do, I understand this decision tree level, and then use that to help guide me through the process. We can use decision trees for classification and regression tasks, and I use these for every single project. No matter what. And also these require very little like data prep. So if I need something like really quick, like let's say during a meeting, like people start having a discussion and a question comes up, I can burn through real quick, grab some data that I have handy, do a decision tree. Towards the end of the meeting, boom, I share the results. I share my screen during my team's meeting, and I get an answer for my stakeholders right then and there. I've done that several times, and that's helped my career quite a bit because I can show that I can, I can answer questions during the meeting instead of having to leave and come back in a week. All right, so let's talk about some, basic concepts. So what is a decision tree? This is like a flowchart-like structure, and we're going to be breaking things down into like yes, no, true, false as we go through my decision tree. So each internal branch represents a test on an attribute that is a predictor variable, and is the predictor variable value above or below a cutoff. Each branch represents the outcome of that test, and each leaf node represents a class label, a decision for the prediction. The path from the root to the leaf represents the classification rules. Now, when I have categorical predictors instead of numeric predictors, then we're going to be saying, hey, is this observation value in this group or this group? It's going to be one of two groups to split. Potentially, for categorical predictors, we have any number of splitting, but typically we always do it in groups. We always do two splits. Some advantages of decision trees are they are simple to understand and interpret. We can visualize them more completely than any other type of model. These require very little data preparation. All right, so other models need to have data normalization. So, center and scale, or making sure that everything's from 0 to 1. Have to convert categorical dummy variables, and we have to deal with outliers. Well, decision trees, like these steps don't hurt us, but they're not as important. All right, so data normalization, it's going to work out that any monotone transformation on my data is not going to improve a decision tree. So I don't need to. That's what makes it so appealing, that and I can get results really fast if I need to, because I don't have to mess with data prep. Also, dummy variables. Now this will depend on the implementation of decision trees. Uh, like Ranger and Random Forest in R, I don't have to do dummy variables. I can just take my categorical data and jump straight in. In Enterprise Miner for SAS, I don't have to do dummy variables. Unfortunately, scikit-learn, I have to do dummy variables. So some implementations of decision trees, random forest, stochastic gradient boosting, I don't have to convert my categorical data into dummy variables. But unfortunately, with scikit-learn, I do. Scikit-learn only accepts numeric values. Now, outliers. When I have outliers, what's going to end up happening is that things are going to get kind of muted down, because when we go through our flowchart and we go down our decision tree, I have a collection of observations in my training data inside a leaf, and they're going to get averaged together. And so what ends up happening is that outliers will just end up in like an extreme leaf, and they end up being like not having the same impact as they would like in like linear regression or logistic regression. It's still best to deal with your outliers, but if I don't, it usually doesn't change that much. That's because decision trees, random forest, and stochastic gradient boosting, any tree-based model does an averaging of the observations in the leaves, or does a voting system. And so when I have something weird going on, it tends to get diluted out. And some implementations of decision trees will handle missing values. Scikit-learn does not. And so there's different ways for it to handle it. Depends on the implementation. One way is to use surrogates to step in when you have a missing value. Another way is to use missing value as a level itself, and on the side of the split. Check your help documentation. Now, it's pretty fast to fit some data with a decision tree. It's pretty quick and easy. Now we can handle both numeric and categorical data. Unfortunately, scikit-learn can only handle numeric values, so I have to do that dummy variable conversion on that one. We can have more than 2 levels for my classifications, and ultimately this is the most white box version of a model possible, and that for any observation I can tell you exactly why we get the prediction that we got by flowing through the tree. Also, we can take our modeling a step further and run hypothesis tests on our leaves. So after I go through my decision tree, I'm going to have data in a leaf, data. So every training observation is going to be inside a leaf, and exactly only one. Well, the leaves define a subpopulation. From that subpopulation, I could do something like ANOVA to check to see if there is a statistically significant difference in the averages of my target variable. I could also do a t-test between 2 different leaves, and I could do a binomial test for different proportions for classification. So if I want to go a step further, this makes it easy for me to be able to do hypothesis testing if I need to be able to defend my results in that manner. Now, okay, so this does not look right. So here, okay, there is an error here, but we'll just keep on rolling. So decision trees tend to perform well even when the assumptions are violated. And also, one thing that I use shallow trees for is that I'll go ahead and build shallow trees that don't that they're underfit, and I know they're going to underperform. Why do I do this? Well, when I go through and I start looking at all the different models I build, I have a benchmark for what is an underperforming model. If the model isn't performing much better than a weak learner, then I know that I got some work to do, or not to use that model structure. It just gives me a benchmark to work with. And also, decision decision trees can handle the situation of very little data, relatively well. Of course, we want as much data as possible, but if somebody walks up and gives me a small data set, make a prediction, it's my job to get results, then I'm going to have to, do something, and a decision tree is a good choice. And I'm going to correct this. There we go. All right. All right. Now, there are disadvantages to decision trees. All right. So it's possible that my tree gets too deep, that I keep on splitting too far, and I can get an overly complex tree and I can overfit. So what we're going to do to protect ourselves from overfitting, we can do pruning. This is how the R part package in R does it, with the complexity parameter. We can also set the minimum number of samples required in a leaf, or minimum number for a split. And we also set the maximum depth of our tree. And so this is necessary to protect ourselves from overfitting. Decision trees can be unstable when I have like very little data in a leaf. And so we can have differences just because of fluctuation in our data. Now, decision trees, the predictions are going to be constant values within the leaf. So when I do my splitting, I get down to the leaf, either it's going to be an average of the training data target variables, or it's going to be it's going to give me like the proportion in the leaf for the target variable classification. And so it's a constant value. So it's not smooth, it's not continuous. And so some people, so this means that I, if I want to, I couldn't like invoke calculus into this. Also, we will never get an extrapolation off of a tree. That's good and bad. Extrapolation is going beyond my observed training data to make a prediction. And so let's say that my independent variable was temperature, and we did science experiment from 70 to 90 degrees, and then I need to make a prediction for 100 degrees. Well, linear regression would go ahead and extrapolate. Generally, we don't want to extrapolate, but if it's the only information we have, we can proceed with take it with a grain of salt. Decision trees will never go larger than the largest average in the tree. And so like the maximum value that I see in my training data is always the largest value I could possibly get off of a decision tree. And so I'll never have extrapolation. That's good in that I'm not, rolling the dice and taking a risk on going outside of my observed data, but it also means that I can't use it in situations where, like it's a little bit beyond what I did for my study. Also, there's no guarantee that we have the optimal decision tree. Computationally, there's no way for us to guarantee that we have the best tree possible given my data. But my experience is that this isn't a big issue. If you play with the parameters, you parameter tuning, you work with it, you'll end up getting something that if it's not optimal, it's close. Now, decision trees can be biased when I have class imbalance. So if I'll probably want to consider balancing my data. Now, something with this is that if I do class balancing, it might be better at classification, but my probabilities won't be reliable. Remember that models always look like they're training data. If I balance my data, then my predicted values are going to look like the balanced data, not the true actual population I drew my data from. All right, so now our criteria for splitting. So for classifiers, we have Gini, entropy, and log loss. For regressor, we have squared error, Friedman's MSE, absolute error, and Poisson. Now, after I have my data all split out, if I have a classification problem and we have tied probabilities in a leaf, then scikit-learn is going to go with the lowest class index in that. So that's just something to be mindful of. So that means that low class index levels for prediction and classification may be appearing more frequently than we intend. This is especially possible if I have a small data set. All right, so now for data preparation, tree models need less data preparation compared to other supervised learning models. Monotone transformations of our predictor variables will not change model performance. So if I took a numeric predictor and I multiplied by a scalar and subtracted by a constant, then I'm going to get the same performance either way. So if I center and scale my data, so I have like mean 0, standard deviation 1, or I rescale my data so that the top predictor variable value is 1, the least is 0, it's not going to change the output. And so I don't need to go through this process if I know that I'm going to just be using a decision tree. Now for ordinal predictors, it ends up that if let's say that I have high, medium, and low. Low was coded as a 1, medium 2, and high as a 3. Now that's ordinal data. Normally, I'm going to need to have to go through and put that over to an ordered categorical variable and convert it over. With decision trees, it doesn't make a difference. I don't have to worry about it because of the way that it splits. It doesn't really matter, and so I don't need to fuss with it. Once again, this saves me time, and this is why I can use these models very quickly, like live during a meeting, and get my stakeholders an answer, within 15 minutes if I have to. Now, some implementations of decision trees can use categorical predictors without converting to dummy variables. Unfortunately, not scikit-learn. And some implementations will handle missing values by replacing with the most frequent category. So there's 3 different ways that they can go with the missing values. Either missing value is its own level in the split, and this can be numeric in some implementations. I think that's how Enterprise Miner does it. It could set, it could use a surrogate to fill in the, to step in, or it can, automatically do imputation. Now, for numeric and ordinal predictors, tree models work by finding the best single split in the data. If k is the number of distinct values, k minus 1 is the number of possible splits. So imagine I have, 1 through 10 is my actual predictor variable values. Well, what the decision tree is going to do is say, hey, should I split between 1 and 2? Should I split between 2 and 3? Should I split between 3 and 4? And all the way down, all the way to should I split between 9 and 10? So if I have k distinct values, k minus 1 is the number of possible splits. All right, well, if you think about that for a moment, you know what? If I have long decimals involved, it's that's going to be more levels to consider. I can speed things up by rounding off my data. And so and that also depends on the implementation. Some implementations do like a random checking when the number of levels is above a certain threshold. Now for categorical predictors, the tree models work to make the best possible partition. If I have k distinct number of levels, it's going to be 2 to the k minus 2 possibilities. All right, so remember, if I have a set, if I have a set of 8 items, then I have 2 to the 8, 256 distinct subsets. All right, so how the tree is going to work is that it's going to try and find the best subset and say, hey, if my observation is in this subset, we go this direction. If it's not in the subset, if it's in the complement, we go the other direction. Okay, well, when it does this, it's not going to consider the empty set, and it's not going to consider the full set. So it's going to be 2 to the k minus 2. So one thing to notice is that if we don't have dummy variables, then that categorical predictor a lot of levels can result in a long computation time. And so you really want to bin your categorical predictor variables before you start modeling. Now, we need to protect ourselves from overfitting. Overfitting can happen when my decision tree gets too deep. And so it can, especially decision trees, they can perform very well in training data, but then do poorly on my validation and test data, my unseen data. And so it'll be capturing noise and fluctuations in the training data. All right, so how do I protect myself from this? Well, first and foremost, the max depth, we just say, hey, don't go very deep. Just stop splitting at a certain point. We can also say, hey, before I split, I need to have a minimum amount of data. In scikit-learn, the default is 2. And we also say the minimum samples in the leaf. All right, so this is the one that I typically use. This is one that I found to be the most effective for random forest in particular. This is the number of observations in a leaf after I split. I need to have at least this many for the split. All right, so now if the max depth is none, then it's going to split until all leaves are pure, or we hit the other 2 criteria for stopping. If the minimum, the default for the minimum sample split is 2, and we can increase that, easily. And the minimum sample leaves has a default of 1. Honestly, I have had a huge improvement on my model performance by just increasing that to 4, which it doesn't seem like a lot, but it has worked out. If I have an integer as the parameter for the split criteria, then that's the minimum number of observations. If I have a float, and so here this needs to be a fraction, this is going to be the minimum proportion of observations in there. And that's true for the minimum for a split or minimum in a leaf. And shallow trees, I like to use shallow trees as a benchmark for like a poor performing model, to make sure that just to compare the models I'm actually going to use. They're fast, it doesn't take a lot of time, especially in scikit-learn. The fit function or the fit method is very consistent across all of the different structures to fit. So it's basically nothing to do this. Also, it helps me understand what's going on because I read through the tree, I understand what's going on. All right, so let's go ahead and do two different examples. Let's do a classification and a regression example. I'm going to use the mushroom data set that I've been using in the videos quite a bit. And for the classification, I want to predict poisonous or edible. And then I'm going to do a sale price for a house in another data set. All right, so here's my distribution of my target variable. So it's not quite 50-50, but it's close. So let's go ahead and do a decision tree classifier. All right, so in my decision tree classifier, this is the one you typically want to use if you're going to be using a decision tree. To show you the extremes, I'm going to just do 2 and none. And so here, the 2 says, hey, stop after 1 or 2 splits, and none says go as deep as you can. And here I'm saying the minimum sample inside the leaf is either 1 or 300. And here I'm just showing you like extreme differences. And so let's go ahead and plot this. All right, so right out of the gate, if I go out into the woods and we see that it has a high odor, one of the high odor categories, then if it's less than or equal to this, then we're going to go one direction and we're going to go the other. All right, so if so here this is saying if it does not have the high odor category, then we go to the left. And so overall, most of them are edible. We can see how many observations we have in there. Here's the the ratio of edible to poisonous. All right, well now if the odor is so here, if the odor is low group, then we go to the left and we conclude that it's edible. Now notice that this is not 100% pure, that there is still a chance of eating, something that's eating a poisonous mushroom. All right, now, let's say that the odor is in the high category, then boom, we immediately say it's poisonous. Now, if the odor is not high, but the odor is moderate, then we say that's poisonous. So I have this flow chart of going through. All right, now if, so this ends up being the same tree. Basically, I've got 4 different trees being built. So a 2x2 grid off of these. So the first 2 are the same. Both of these have a depth of 2. Now it's getting a little bit more interesting. You can see that so these are done. Both of these are 100% pure. They say poisonous. If I reach this node, if I reach this leaf, either one of these, then it's poisonous. I have pure leaf. There's nothing to split anymore. Now, if I was to come here in the previous tree and split this, well, you know what? I can get this to be pure 100% by taking the stalk shape, considering it, if it's not, the stalk shape is not high, then it's going to be 100% edible. And here we have it's still overwhelmingly edible, but it's not, I was able to make this leaf more pure than over here. And now here we get, now we can just keep on going with this and keep on getting deeper and deeper and deeper until we get, what we finally want. All right, now let's talk about extra tree classifier. Extra tree classifier, typically we don't actually use. This involves some randomness into it, and we typically use this in other modeling techniques where we take a collection of trees and create an ensemble, it's called an ensemble model, to get a more powerful model overall than a single decision tree would give us. It's freely available. I use it as a benchmark, once again, as a weak performing model. This just so that I have a better understanding of how well is my model performing when I'm doing like the better performing models. So these differ from classic decision trees in the way that they're built. When looking for the best split to separate the sample of a node into 2 groups, random splits are drawn for each of the max features, randomly selected features, and the best split among those are chosen. When max features is set to 1, this amounts to building a totally random decision tree. All right, so warning, extra trees should only be used within ensemble models. All right, so that's for actual like production. I use them as a benchmark just so that I can see, hey, I know that this model is not going to perform very well. Let's compare it to, my random forest, my k nearest neighbors, my linear regression model, whatever, support vector machines. I can compare my other models to it because I know that this one should be the weaker one. All right, and so here I'm going through and, we can see that these are definitely like deeper right out of the gate. What I set for, all right, so here I set up the max features as 1 square root log 2 or none. And so this was the only parameter that I messed with on this one. And you can see that these are all much, much more complicated trees. And these are all different than what we had for the regular decision tree. All right, so now let's go ahead and get the predicted value. So what I'm going to do, I'm going to take the list of models I have for decision trees and the list of extra tree classifiers, put them together into one list. So remember that if I add 2 lists together, they just concatenate in Python. Now I'm going to get the predictions for each of these. And so now I'm going to get the modeled probabilities of each of these. And I've got it nice and clean in a data frame. Now let's go ahead and evaluate my train, validation, and test statistics. And so here, I'm going off of AUC. So a bunch of these ended up being perfect AUCs, across the board. Now that's not because I have a great model or I did a good job. That's because the odor predictor variable is so powerful that it's making these models look better than they really are. Normally I'm not going to have results that good, but this is what I do at work, where I'll have my train, my test, my validation. I'll sort them, and then I'll start looking to see which one's the best one to actually work with. Now for regression, let's go ahead and use the house prices data set. And this is the prepared version I already did. Like for example, I did Box-Cox transformation, Box-Cox or Yo-Johnson on the target variable. And so we can see the distribution. So this is house prices after an exponential transform. And then let's go ahead and use a decision tree regressor. And so now, all right, so if the overall quality is less than or equal to 0.3, now this is the prepared version of it, then I'm going to be going to the left. And so remember, I centered and scaled numeric predictor variables. If overall quality is greater than 0.312, I go to the right. All right, so if the ground living area is less than negative 0.227, I go to the left. If it's greater than negative 0.227, I go to the right. If the garage cars is less than or equal to 0.982, I go to the left. If it's greater than or equal to 0.982, I go to the right. And so you can see, now something that's nice about this is that the orange tells us how pure things are, or what the average is. And we can see that we have the least value going up to here. And so all the 65 samples here, my training data, have an average of 12.6. Here I have an average of 12.2, average of 11.98, and an average of 11.7. All right. And so the reason why I like shallow trees is this immediately tells me that overall quality, ground living area, and garage cars are going to be important predictor variables overall. Now, garage cars, when I looked at that on its own by itself, it wasn't that important. When I look at garage cars here, that's after considering overall quality, garage cars becomes important. So I know that more than likely I'm going to want to keep garage cars in my model, even though individually it didn't look like it was going to be a strong predictor. It's adding value when other strong predictor variables are present. All right, so we get the same model. All right, now things are going a little bit deeper. And you use the orange to get an idea of which leaves have the largest average and which ones have the least. And here I definitely have overfitted on this one. Now, extra tree regressor. Once again, I'm not going to use this in production, but this is a good benchmark to compare my models with. And for some reason, this did not display. All right, here we go. And so here I have my shallow tree, getting a little bit more complicated. Now you'll notice I have different predictor variables involved because of that random aspect of the extra tree. So here it's neighborhood, high or low, garage cars, overall quality. And so this random aspect, it doesn't have, it's not taking full advantage of the entire data set. It's taking a subset of the predictors and randomly picking them. And so, we'll end up getting different models every single time. Now, the predictor variables that get picked frequently, that's an indication that that predictor variable is more important. If I keep on building tree after tree after tree, now I'm going to do the same trick I did before. And now I've got everything set up nicely. I can go through and I can check to see which one has the least mean squared error. All right, well, it ended up being an extra tree regressor. And so then here I have decision tree regressor. And so you notice that real quickly, minimum sample leaf is 15. And I can just scroll through and look to see which one would be best. All right, so we went over decision trees. I love decision trees. Decision trees, because of that lack of data prep, I can use those on the fly real quick in real time to get results to my stakeholders. That has helped my career a lot because I can give them an answer in the moment. We're talking with our stakeholders. Stakeholder says something, oh, I wonder about XYZ. I immediately grab the data that I have, get it going, get a decision tree, plot it, put it in front of my stakeholders. I have an answer like that. And this has helped, increase my credibility at work by quite a bit. And so I feel like decision trees are, definitely something that you want to be, super proficient with to be able to get results fast. That very low data prep also makes it that if I needed to get a model out the door very, very quickly, I could, putting less time and effort into data prep, I could do a decision tree, I could do a random forest, stochastic gradient boosting, something like that, and get a model out real faster than, the other types of modeling. Huge advantages. I love this. Decision trees on their own tend to not be as powerful as other models, but as you can see, there's distinct advantages. Well, that's all I've got for you. Life is short. Do math.